Okay, students, so the next experiment we're going to work on is on gamma ray attenuation. And let me just tell you what that's about. We have a gamma ray source that's sitting right here. It's a cesium-137 with the 663 keV gamma ray coming out. And if I put the audio Geiger counter over it, of course you can hear all the counts coming out. And I'll leave it on just for a minute there so you can sort of get a sense for how many counts are coming in, clicking away there. And of course what I can do then is I can take something like a piece of lead here, which is about 1/4 inch thick, put it over the gamma ray source, and then put the detector on top of that. And you can tell maybe the counts are a bit less. And if I take another piece of lead and put it over that one, so now I have 2 lead plates on there. The counts are definitely less now. And I can take a third piece and put it over. The counts are definitely lower. So that's what shielding is all about, that we'll be studying in this lab, is if you take a bunch of materials, say like this lead here, what exactly is the gamma ray going to do? Well, it's sort of here's the piece of lead here, and the gamma ray is going to come and approach the lead. So what happens inside the lead that prevents the gamma ray from going through? Well, that's sort of the big question. But at the energy of cesium-137, the 663 keV gamma ray, the primary processes that remove gamma rays from a beam, so if the gamma rays are coming up this way and going through the lead, apparently they're not emerging as much as they did when there was just air here. They're not emerging from the lead, and the 2 primary processes that take them out of the beam at this energy are Compton scattering, of course, and photoelectric absorption. And so those 2 processes are what are removing gamma rays from the outgoing beam that would normally just go right up into the detector. Put a piece of lead on, suddenly there's a lot of electrons around for photoelectric absorption and Compton scattering, and not as many gamma rays emerge from the lead and continue on their way. So that's what we're going to study in this experiment. The setup is going to be conceptually pretty simple. So all we've sort of done here is taken the normal gamma ray setup that you're used to. We have the detector here just turned upside down, and we'll put the source sort of down like this in front of the detector, or below the detector. You can see it right there. And you can see over on the oscilloscope screen that you have your normal gamma ray signal coming in. You can see that over there in the back. Okay, normal. If I took a spectrum, you see cesium-137. But what we've done in this case here is we've just left a little gap here between the source and the detector. So it does a couple things for us. It definitely sort of weakens the rate at which we observe gamma rays, because now the gamma rays are sort of spreading out and going all over. They're not all going right into the detector. So our counts are a little less, but nonetheless we need a little space to work with here. And so what we're going to do is we're going to take a gamma ray spectrum like this, say with just air in between, an air gap in there. So nothing much is going to happen. That would be unexpected because there's no attenuation going on. Then we're going to put 1 lead plate in the way and repeat the spectrum. Take another one. Then we're going to put another lead plate in the way, take a spectrum again. And put another lead plate in the way and take a spectrum again. And what we're going to find is we're always going to take the spectrum for the same amount of time. In this case, 5 minutes seems adequate, and I'll show you why in the next video. And so we're just going to put these lead plates between the source and the detector and wait 5 minutes and see how many gamma rays we get each time. And of course you're going to expect the amount to go down, and we're going to study systematically how the rate of gamma rays goes down as a function of total thickness of absorbing material that we placed between the gamma ray source and the detector. So that's about it. We're going to make a plot of gamma rays received versus thickness of material and see what we get. And it turns out we can derive a very particular quantity about the material called the attenuation coefficient. These grayish plates here are of course lead. Those are probably the first thing you think of when you think of shielding. But we can also say put something like a piece of aluminum in there. So we'll look at aluminum as well. And we can definitely expose different gamma ray interaction parameters of lead versus aluminum in the experiment. So that's what we'll work on. So again, core data is going to be number of gamma rays received at the detector over a common time interval as a function of the thickness of the material that you have between the source and the detector. So in the next video, I'll sort of show you how we set up the software and get the process going.